Good evening. I want to talk to you about a very special star. It's by no means outstandingly brilliant. In fact, if you don't count the sun, it's only the 48th brightest star in the entire sky. Not at all outstanding. But it is of special significance to us. It is Polaris, the pole star, in the constellation of Ursa Minor, the Little Bear. And to start things off, here is a photograph for the constellation taken by Commander Hatfield. And there are two fairly bright stars in it. Over to the right-hand side of your screen, you can see Polaris, and over to the left-hand side, the other reasonably bright star of the Little Bear, which is called Kochab. And in fact, those two stars are not alike, because Polaris is white. Actually, it's very slightly yellowish, but frankly, it always looks white to me. And Kochab is decidedly orange. And you can see that difference even with the naked eye, and if you use binoculars, it comes out very strongly. And the answer is quite simple. Kochab has a surface which is not so hot as that of Polaris. But why is Polaris so significant? And the answer is that, within a degree, it marks the north pole of the sky. And therefore, it seems to stay virtually still with everything else going round it once in 24 hours. And I will show you why. As I think everybody now knows, the Earth is a globe, nearly 8,000 miles in diameter, going around the sun at a distance of 93 million miles. It spins on its axis once in approximately 24 hours. And it so happens that in a northerly direction, the axis points to a position in the sky, the north celestial pole, which is within 1 degree of Polaris. Now just imagine that you're standing at the North Pole. Polaris then is straight above your head. And as the Earth spins, Polaris doesn't move. Everything else seems to go around it. And because the Earth spins on its axis from west to east, the sky appears to go round from east to west. Now, there's another point, too. The apparent altitude of Polaris, that's to say the height above the horizon, tells you your latitude on the Earth's surface. The latitude at any particular place is your angular distance north or south of the celestial equator. In the case of the pole, of course, it's 90 degrees. In London, well, it's roughly 51 degrees. And as you can see from this diagram, that also means that the altitude of Polaris is also 51 degrees. Because although Polaris is not at an infinite distance, it is so far away that you can say that, to all intents and purposes, those two lines are parallel. That means that if you want to find your latitude on the Earth's surface, all you have to do is to measure the apparent height of Polaris above the horizon. And all through the ages, navigators have found that very useful indeed. So find your latitude, find the altitude of Polaris, and there you are. Finding your longitude is rather different, but that's quite another story. But there is one small correction to be made. Polaris is not absolutely at the pole of the sky. It's rather less than 1 degree off. And you can prove that very easily if you take an ordinary camera, any camera to give you time exposure, go out at night on a clear night, point it north, and leave the shutter open. And as the Earth spins round, so the stars will appear to move across your photographic plate, and they will leave trails. And there is a polar trail. And as you can see, that little thing that looks like rather a banana, just above the center of the picture, that is the trail left by Polaris. Now, if Polaris were exactly at the pole of the sky, then it would leave a sharp point. But it's not. As I say, rather less than 1 degree away. And the other trails are longer because the stars are further from the pole. And here's another picture showing the northern part of the sky. And as you can see, the further away you are from the pole, which is near the bottom of the picture, the longer those star trails are. And that's a very easy way of showing the Earth's motion. And also, it means that once you've located the pole star, you can always find it again, because to all intents and purposes, it doesn't move. But there is another way of finding it too, a very easy one, and that's by using the most famous constellation in the entire sky, which is Ursa Major, or the Great Bear, which some people call the Plough. And I think everybody can recognize that, particularly since from here it never actually sets. Now, the two end stars of Ursa Major are called Merak and Dupe. And once again, they're slightly different in color. If you use binoculars and look at them one after the other, you will see that Merak is white and Dupe is decidedly orange. Now, they are known as the pointers because they show the way to the pole star. if you take a line from Merak, pass it through Dieppe and extend it, then you will come to Polaris, and you can't mistake it. The actual position of the pole, not absolutely coincident with Polaris, is in the general direction of the end of the Great Bear. But to all intents and purposes, you can say it is at the pole. Now, those two constellations, Ursa Major, the Great Bear, and Ursa Minor, the Little Bear, are very famous, and obviously there is a legend about them. Remember, a constellation is not really an associated group of stars, simply because the stars are at very different distances from us, and we are dealing simply with line-of-sight effects. But the ancients imagined they could see patterns there, and that they saw bears in these two constellations. And the legend goes like this. The Great Bear, Ursa Major, was originally a beautiful princess whose name was Callisto, and she was really lovely. In fact, she was so beautiful that her beauty was greater than that of Juno, the queen of Olympus. And Juno was not noted for her pleasant nature, and she was so infuriated by this that she changed the poor princess into a bear. Years later, her son, Arcas, was out hunting when he saw the bear, and not realizing it was his fond mother, he took out his bow and arrow and was about to shoot it, when Jupiter, the king of Olympus, looked down, saw what was happening, and intervened. And to save them both, he reached down, picked the animals up by their tails, changed Arcas into a bear also, and swung them into the sky. And that is where you see them today. And that is why Ursa Major and Ursa Minor do have rather unbear-like tails. And when you look at the two pictures of them, well, it's rather difficult, I think, to make a bear out of that. But nevertheless, they did so. But I think, on the whole, the description of the plough for the Great Bear is rather better. And you can see Ursa Minor looks like a rather faint and distorted version coming down over the Great Bear's tail. And when you see a photograph of Ursa Major itself, it is really pretty distinctive. The stars are not outstandingly bright, but they do make up a well-defined pattern, and from Britain you can always see them whenever the sky is sufficiently dark and clear, because they're what's known as circumpolar stars. Now remember, to all intents and purposes, the pole star remains still, and everything else goes round it. And it depends whether your stars do, or do not, drop below the horizon. Well, let's have a look. Here is a diagram. There in the middle is the Little Bear with Polaris. And you can see the Great Bear, and on the opposite side, the W of Cassiopeia. And as the sky goes round, so these constellations go round the pole. But now follow the bear's tail round, you see a much brighter star called Arcturus. And that dips down below the horizon. So for part of the 24-hour rotation, Arcturus is below the horizon, but the Great Bear is not. And there Arcturus is reappearing again. Of course, we've speeded this up very much because the Earth takes about 24 hours to go round, and we are doing it in a few seconds. But you can see what happens. So the Great Bear and the Little Bear are always above the horizon, and the Great Bear can pass overhead. But of course, as you go further south toward the equator, so the Great Bear and Polaris become lower in the sky. I said a little while ago that your latitude on the Earth depends upon the altitude of Polaris. So from London, about 51 degrees. Go down further south, your latitude is lower, and Polaris is lower. By the time you get to the equator, latitude 0 degrees, the altitude of the Polaris is also 0 degrees. In other words, it's right on the horizon. And if you go south of the equator, you can't see it at all. So southern navigators can't use our own particular pole star. I'll come back to that later on. But remember, Polaris is not really important in itself. It is simply important to us because it lies so close to the pole of the sky. But it hasn't always done so, and it won't always do so, because the Earth's axis doesn't point in a constant direction. It topples a bit. It's what we call a precession, and the behavior is rather like that of a gyroscope, which is toppling. And watch this gyroscope as it spins. You can see the top there, and what the top of the axis, and as the gyroscope spins round, that axis wobbles. It describes a circle. And of course here it's doing that in a very few seconds. Well, the Earth is doing exactly the same thing. It's acting rather in the way of a gyroscope, and the axis is moving round just as that of the gyroscope did. Only instead of taking a few seconds, it takes something like 24,000 years to do so. Nevertheless, there is a definite notion there, and if the Earth's axis points in a different direction over the centuries, then the position of the pole of the sky is going to also too. And it does alter, and that's happened in historic times. And here we can see the wandering of the pole. Over to the right-hand side, Ursa Major, the Great Bear, see Polaris too, and that yellow circle indicates how the pole moves over the centuries. And at the moment, coming up to AD 2000, it's very close to Polaris. It'll actually be at its very closest to Polaris in something like 100 years from now. But now look back to about 2500 BC, the time when the Egyptian pyramids were built. And the pole was not then near Polaris at all. It was near a very much fainter star called Thuban in the constellation of the Dragon. And therefore the Egyptian pyramid passages were lined up not with Polaris, but with Thuban in Draco the Dragon. So let's find Thuban. First of all, come back to the pointers, and they show the way to Polaris. Near the pole now, it wasn't in Egyptian times. And now look at the end star of Ursa Major, which is called Alkaid. And between those two, there lies a very much fainter star, and that is Thuban, about as bright as the faintest of the 7 stars in the Great Bear. And in fact, Thuban is by no means outstanding, but it was the pole star in Egyptian times. And the Dragon, well, the Dragon, another northern constellation, not really conspicuous, but that's how the ancients imagined it to be. It's a long constellation. We see there also the Little Bear and the Great Bear, and there are the stars of the Dragon, which are by no means outstanding, but in fact it wanders in between the 2 bears. So Thuban was the pole star in Egyptian times, and now the pole star is our own Polaris. So let's go back to our diagram and see what's going to happen next. Well, very slowly, the pole moves. It's going past Polaris, and in something like 10,000 years from now, the pole will wander around and become close to the bright star Deneb in the constellation of Cygnus the Swan. It will then progress, and in about 14,000 years, it will be near a very brilliant star indeed, Vega, in the constellation of Lyra of the Lyre. And then we really will have a splendid pole star, because Vega is very bright. And here's a photograph of that constellation, Lyra, taken by Ron Arbour, and you can see that Vega is very much the brightest star in it. It's rather on its own. And Vega is also very easy to identify. It's almost overhead in summer evenings from here. It's very bright, one of the brightest stars in the sky, much brighter than Polaris. It's also decidedly blue, so it has a very hot kind of surface. And incidentally, it is about 50 times as powerful as our Sun. So in 14,000 years, we'll have a really good pole star. Then, of course, the pole will go on, wandering around in its circle, and it'll pass by Thuban, and then finally come back to where it is now, and Polaris will again be the pole star. But that movement is very slow. I say it takes 26,000 years to go right round. So Polaris is going to be the pole star in your time, and mine, and your children, and your great-great-great-grandchildren. So let's now have a look at Polaris itself. What kind of a star is it? Well, to start with, it's a white star, or very slightly yellowish, which means its surface is rather hotter than that of the Sun. It is of the 2nd magnitude. Now, the stars in the sky are divided into grades, or magnitudes, of apparent brilliancy. And I don't mean real luminosity. That may or may not be associated with it. But Polaris is of the 2nd magnitude, which means it's reasonably bright, because the scale works rather in the way of a golfer's handicap, with the more brilliant performers having the lower values. And Vega is about magnitude 0, and Rigel and Betelgeuse and Orion are 1, and most of the leading stars in the Great Bear and Polaris are of magnitude 2. But the rest of the stars in the Little Bear, apart from Kochab, are fainter than that. And you can see them here again, Polaris over to the right, Kochab over to the left, and the other stars are pretty faint. They're between magnitudes 3 and below 4. And that means, of course, that if you have any misty sky, well, you won't see them at all, and the Little Bear is not really identifiable. But there they are. So Polaris is of magnitude 2. But it's not absolutely constant in brightness. Most stars, including the Sun, luckily, shine steadily for year after year, century after century. But there are some stars which are variable. They pulsate in and out. And Polaris is one of those. It's what's called a Cepheid variable star. So its output does change slightly, and it swells and shrinks. And it does so in a period of just under 4 days. But the magnitude changes are very slight indeed, and frankly, you're not going to notice them. It is very slightly a variable star. Now, what about its distance? Earlier on, I said that it's so far away that, to all practical purposes, you can say it's infinitely distant. Well, of course, that's not really true, because the stars are not infinitely distant, and Polaris is about 680 light years away. Now, in astronomy, we have to deal with immense distances and immense spans of time. And there's no real point in trying to measure the star's distances in miles or kilometers, because the figures would be uncomfortably large. In just the same way, you could, I suppose, measure the distance between London and Birmingham in inches or centimeters. But it would be very clumsy, because those units are too short to be convenient. And the same is true of the mile or the kilometer when you're talking about the stars. So instead we use the light year. And a light year is the distance traveled by a ray of light in 1 year. And since light goes along at 186,000 miles a second, 1 light year is nearly 6 million miles. And so Polaris, 680 light years away, we are seeing it not as it is now, but as it used to be 680 years ago. And if some unkind genii suddenly snatched Polaris out of the sky, we wouldn't know for another 680 years. But if it's that far away, and also looks reasonably bright, then it must be powerful. And in fact it is. It's about 6,000 times as powerful as our sun, so it's quite a powerful star. And also, it's not a star which is alone. It has a small companion. And the other night, I made a drawing of that with my own telescope, and there it is, the bright star there, and close by it is a 9th magnitude faint companion, which is not easy to see except when you have a telescope. Then you can't see it at all with binoculars, and a 3-inch telescope will just about show it. And it really is a genuine companion of Polaris, but of course the two are a long way apart, thousands of millions of miles apart. But they're going through space together, and no doubt they did have a common origin. And I just wonder, what would we see if we could go close to Polaris and have a look? So let's do so in imagination. And here's a Pole Dirty drawing. There we start off with a companion star, and then we come on to Polaris itself. And I just wonder whether there are any planets in the Polaris system. On the whole, I rather doubt it, because Polaris may be too energetic a star, but I suppose that could be so, and if anyone does live on a planet in the Polaris system, that might be the kind of thing they would see, with the sun emerging from behind an obscuring body. But of course, from there, our sun would appear very much less brilliant than Polaris does to us, because remember, Polaris is 6,000 times as bright as the sun. Well, we are very familiar with our pole star, but remember earlier on, I said that if you go down to the equator, the altitude will be 0, and further south from that, you can't see Polaris at all. There is a south polar star, but it's very faint. And here's a picture of star trails I took from the southern hemisphere some time ago. The South Pole is just about in the middle of the picture, and as you can see, there's no bright star there. So the Southern Hemisphere navigators are not able to use our own pole star, and they haven't got one of their own, at least not a very good one. Their pole star, Sigma Octantis, is very obscure indeed, and so I think we've every reason to be proud of our own pole star. And it's going to remain marking the North Pole of the sky for a long, long time to come, and navigators are going to go on finding it useful. Before I go, don't forget our Sky at Night information line. If you want the latest astronomical news, ring up 0836 406075, or of course, dial CFAX page 616. Good night.